Yes, if you have any questions, please ask. Sweta, good afternoon. Please ask your question. Okay, so coherence length is actually a quantity. It's a length scale of say a superconductor. If you're asking in the context of superconductivity, so it just tells you that when you have a Cooper pair, that is two electrons forming a bound pair, which is induced by the phonon, rather the electron phonon interaction. So this Cooper pair is a quantum mechanical object, okay, and this Cooper pair has it can be treated as a composite particle, and by de Broglie's principle, every particle will have a wave description. So say even the Cooper pair will have a wave description. So this coherence length is actually the say the the extent of the wave function for the Cooper pair. Or you can also see it in this fashion, that if you have an electron at a given place, say R, or given site R, what is the maximum distance that another electron at R prime would form a Cooper pair with it? Okay, so that distance, that maximum distance, is called as the coherence length. It's a nice quantity that distinguishes the the type 1 and type 2 superconductors. So for example, in one kind of superconductor, you have the coherence length is almost like 5,000 angstrom, whereas in the the other kind of superconductor, you have a smaller coherence length. So it's basically, there is something called a penetration depth that we have talked about, and so this, that is another length scale of the problem. I mean, that tells you how much the magnetic field penetrates inside the superconducting sample. So I hope your question on coherence length is clear. It's the distance over which the extent of the Cooper pair wave function, or rather, that's the length scale for the Cooper pair wave function. So if you draw a wave, that's where I mean it extends from one place to another, and that's called as coherence length. Others, please ask questions. Thank you. Lokesh, yes. Good afternoon. Go ahead, ask your question. That's a good question, Shweta. So in BCS theory, the specific heat capacity jump means that there is a transition from a superconducting state to a normal state. Okay, and specific heat, if you go back to your statistical mechanics, it's the second derivative of the free energy with respect to temperature, and the theory of phase transition says that whichever derivative becomes discontinuous, that's denotes the order of the phase transition. So because the specific heat is discontinuous, which means the second derivative of free energy is discontinuous, um, so that's a second order phase transition. So the phase gets transformed um, from a metallic state to a superconducting state, or if you go from low temperature regime, it changes from superconducting to normal. So that's what the specific heat jump means. uh, Lokesh, I have no idea about your question. Information in NPTEL course. So, what is detailed information? You should write to NPTEL Madras. Shohini Chakravarti, yes, the weak coupling. I don't know exactly which context you are asking, but so suppose there's a Hamiltonian which has two terms, which is one is a kinetic energy, let's call that by T or K, whatever you want to call it, say call it T, and there's an interaction term which is U. So the weak coupling is when U is much smaller than T. So that's called as a weak coupling. The coupling between the electrons or the interparticle interaction is weak. That's called as weak coupling. And so the kinetic energy is larger. So in those cases, mostly perturbation theory or something like a mean field theory works well. Now, BCS theory is really a weak coupling theory, but it so happens that the energy correction, or rather the two particle bound state energy, assumes a form which is quite non-intuitive. It goes at exponential minus 1 by that n naught v, where n naught is the density of states at the Fermi level. Because of this, even BCS theory being weak coupling, perturbation theory doesn't work because of this. Something that is there for the two particle energies. But in general, in other weak coupling theories, the mean field theory or the perturbation theory works. Yes, Shweta. There should not be an issue. I will. You can mention your roll number and just write an email to me. I will forward it to the TAs who do the correction of the assignments. But should not be a problem if you have written your roll number or your whatever ID number. Should not be a problem. Shoini, if that is clear, you can ask more on this if you wish. Okay. All right. Thank you. Uh, Sweta, that's a question that, so what happens is that, as I just told to Shohini's question, that on the weak coupling issue, so one doesn't use, a priori, of course, you don't know whether to use a perturbation theory, but the only other alternative for solving a problem when you don't know the exact solution is using a variational theory. Okay, so variational theory is a theory in which there is a free parameter in the Hamiltonian. Okay, and then you write down by your intuition, or not in the Hamiltonian, sorry, the Hamiltonian doesn't have a free parameter, but by intuition you write down a wave function which has a free parameter. Now you calculate the energy because I mean basically the expectation value of the Hamiltonian with respect to the variational state that you have written down purely from intuition and from symmetry arguments. So you don't need to do a perturbation theory. You don't need to do a mean field theory. You can do a variational theory, which is it is not clear how why variational calculations are most of the time um, they are effective. They are only effective when you have identified the wave function. In this particular case, we have identified the wave function, which is called the BCS wave function, which has got two variational parameters, UK and VK. Then we calculated the expectation value of the BCS Hamiltonian with respect to these BCS state, and there these two variational parameters UK and VK, we could actually do a minimization of the free energy with respect to UK and VK. But it turns out because UK square plus VK square equal to 1, so there is only one independent variational parameter, and which is which we have called it as theta k, because UK square plus VK square plus equal to 1 means that there should be they should be, I mean we should be able to write it down in terms of sine square theta and cos square theta. So theta becomes a variational parameter, and then we have um, went ahead and did a minimization of the free energy, calculated the energy of the two particle state, and then we have gone to finite temperature just by identifying the Fermi function, and from there we calculated the expectation value of these quasi-particle operators. Yes, that's a good question, Shohini. The value of 2 delta by KTC for high temperature superconductor is quite large. It's 8 to 10. Something like 8 or 9 or 10, or even could be larger than that. Whereas for BCS superconductor, it's 3.52. So this is something again strange, that it doesn't matter which superconductor you talk about. When you take the energy gap 2 delta by this KTC, K is the Boltzmann constant and TC is the transition temperature. So your delta and TC, they change with from one superconductor to another, but this ratio remains constant. It's just about 3.5 to 3.52 for BCS. For high temperature, it's about 8 to 10. All right. Any other question? Anything else? Okay, this is, I think I have explained it properly in the class. Uh, so what happens is that uh, you have the Hamiltonian and which you have to solve basically, and because it's a many body Hamiltonian, you cannot solve it exactly by the normal methods or that is known to you. So you resort to some kind of variational theory, which is what I explained. And after that, when you went to finite temperature, because just doing the calculation at zero temperature will tell you how the gap actually scales with chemical potential, but it doesn't tell you the gap, the temperature dependence of the gap. For that, you have to go to finite temperature. Now, when you go to finite temperature and you want to write down the Hamiltonian, again you can do the variational theory and solve the problem. But what we did instead is that we wrote down a transformation which is called as a Bogoliubov-Vallothin transformation. And if you apply that transformation to the Hamiltonian, the Hamiltonian becomes diagonal in terms of the quasi-particle operators. Now, this is something slightly tricky, and if one doesn't know, then it's very hard to do that. So this is what the Bogoliubov transformation or Bogoliubov-Vallothin transformation is known for. But it doesn't. The story doesn't end there. When you do this transformation, you have to put the there'll be terms such as gamma dagger, gamma dagger, gamma dagger, gamma, gamma, gamma dagger, and gamma, gamma. Now the coefficients of gamma dagger, and gamma, gamma should go to 0. But just putting them equal to 0 doesn't help. So you have to collect the coefficients of gamma dagger, gamma dagger. Gamma is the quasi-particle. They are the quasi-particle operators. So you collect the coefficients of gamma dagger, and gamma, gamma, and collect them and see that they actually satisfy the equations that we have already said in terms of UK and VK. So if you look at the definitions of UK and VK, as we have told in the during the class, so they are these equal to 0, that is the coefficients of the off diagonal term equal to 0. That tells you that so this transformation is valid and it indeed makes the Hamiltonian diagonal. So that's why this is the quasi-particle operators, or this transformation actually diagonalizes the Hamiltonian. Thank you. Shweta and Sohini, where are you from and what are you doing? Um, pattern of the question paper will be exactly similar or very similar to the assignment paper. You have to write the final result, and so they are mostly from the assignments and whatever we have discussed in the class. So if you follow the class material properly and also solve the tutorials or assignments, I think then there should be no problem. Oh, very nice. Okay. So is it theoretical condensed matter physics or you've done experiments? Anyway, just I hope that this course is going to be, sort of useful for you for your understanding of superconductivity and in general condensed matter physics. So how interacting systems are dealt with, and why do we need this Green's function technique and so on. Okay. All right. Please tell me if you have some more questions. Okay. Yeah, the contents are little difficult, but this is, in the sense that if you want to understand interacting systems, which is not taught in the first course of solid state physics. First course on solid state physics only teaches you how to deal with non-interacting systems. So this is the first course where interactions are brought into the system, and we get a chance to deal with many body problems. Okay. So that's why the formalism becomes a little, tedious in terms of algebra. But once you get a hang of, these physics, I think then should not be a problem. Anyone else? Thank you, Sweta. Anyone else has a question? So please ask me questions, because if we do not have any more questions, then we might wind up. Okay, maybe we'll just wait for 2 more minutes. Okay, all right. Since there are no more questions, let's wind up.